Hello and welcome to a new FLUXANA webinar in our Inside XRF series. My name is Susan Aschenbrenner. Today I'm going to talk about fluxes in Fusion. I will give you some tips and tricks for choosing your right flux and how to use additives correctly. So let's dive into it. First of all, let's have a look how to get this into the greater context. So we are talking about sample preparation today. We are talking about fusion fluxes, so we are talking about fusion. And that means having a solid sample prepared as a fused bead. What's the basics principle behind this is we are having some sample, some kind of powder sample. We are having a dilutant that can be glass forming like a lithium borate. We mix it, we get our mixture for the fusion. The mixture goes into a crucible. We are maybe adding some additive. I'm talking about that in detail later. We are then having the fusion process. And in the end, hopefully, we get such a nice fused bead here. So what's our aim here? We want to have a bead that looks like that. We want to have a perfect surface, no bubbles, no particles, nothing that can somehow disturb our measurement in the end, just some perfect bead. How can this be done? There are some ways how this can be done. First of all, there is the manual way, just to do it in a muffle furnace. You can do it in an automatic muffle furnace like our Vitriox electric devices you can see over here. There are also induction furnaces in the market. And there are also very traditional fusion machines that run with gas, like our Vitriox gas machines you can see down here on the right. So now fluxes. What's important when you are choosing your fusion flux for your process? First of all, if possible, we want the flux to be glass forming because in the end, we want to have a glass. Then you want the flux to have little impurities because this is your dilutant. And every impurity that you see in your dilutant, you will later see in your measurement, in your analysis. And you might have to correct for them later. So you try to have just little impurities in your fusion flux. Another very important point is that the flux shall not be hygroscopic or just little hygroscopic. This you can reach by using pre-melted fluxes, or you have to dry them before every use. So the pre-melted flux is maybe a little bit efficient there. Why is that so important? When there's water inside your flux and you use it in fusion, the water will go away and you will have different dilutions with every preparation. And this will result in poor precision there. Maybe a little bit more to this, the more lithium metaborate is in your flux, we will talk about this later as well, the more hygroscopic it will get. So keep that in mind. And then you want the flux to have a low melting point and viscosity. We will talk about this in detail later too. And the thing that does all of this is borates. Let's also talk a little bit about automatical dosing systems and the special requirements we are having to fluxes there, because automatical dosing systems are more and more coming up in the market. And here it's even more important to have a flux that is non-hygroscopic because we don't want to have clumps inside of our machine. Then it has to be as dust-free as possible. And for some automatical dosing systems, just like our Boramat, you can see over here, the flux has to be ball shapes, just looking like small little pearls. So which fluxes are typical for XRF sample preparation? First of all, let's talk a little bit about the past. In the past, sodium tetraborate was used, But today this is substituted by lithium tetraborate. Why? Because we want to analyze sodium, or you can analyze sodium, and this will not be possible when you're using sodium tetraborate like very easily. So which kinds of fluxes are used then? We already talked about lithium tetraborate. You can see this here in my little table with typical fluxes as well. Then we are having lithium metaborate down here. Lithium metaborate is actually not typically used in XRF sample preparation, but more for ICP. But what is used in XRF sample preparation is mixtures between both of them. So this is why I put it here as well. So we are having lithium tetraborate, lithium metaborate, and a lot of mixtures in between. We just put the most typical ones here in this table to not make it very large. And here you can see two important points in the table as well. We want the flux to be glass forming and having a low melting point. I already said it in the slide before. And we can see here that the more metaborate we are having in our fusion flux, the less glass forming it will be. And the more metaborate we are having in our fusion flux, the lower the melting point will be. I can also show it in this way. This might be a little bit easier to comprehend. And here we actually see the same thing. I substituted temperature, the melting temperature by viscosity in melt here, because this is what the melting point tells us how viscous the material will be in the melt. But let's first talk about glass forming ability of the fluxes. Maybe you already saw something like this when you are talking about fusion, and if you're doing fusion in your lab. What is this? This is a crystallized bead. How does this happen? We don't have enough glass forming ability in our flux, for example. This would be then based on recipe. As well, there might be something wrong with your cooling conditions, or you might have a scratch in your mold. So there's also a way to tackle this problem based on the fusion technique. Always keep that in mind, that it might also happen due to something that is going wrong in your fusion technique. So cooling conditions, very important part, and also the mold should have a nice surface. So, but we are talking about flux today. So we are coming back with our very nice table here. And we can see that the glass forming ability of the lithium tetraborate is the highest glass forming ability we are having here. And it decreases the more metaborate is in the flux. So each mixture here that contains more and more metaborate will have less glass forming ability. And that's when something like this happens, this crystallization, when it cannot form a glass anymore, and you will have just some crystal structure here. What does that mean in the end? These fluxes are rather suitable for samples that already contain glass forming agents. So there are samples that, for example, contain a lot of silicon dioxide. Silicon dioxide is a glass forming agent. When a sample like this is on your table, you might also go for fluxes that have a high part of lithium metaborate, because it will still build a glass. So the next point is viscosity in melt. We will move on to that now. So here you can see a broken bead. I guess everybody who does fusion and has just little critical samples knows what that looks like, but I still put some picture here. And how does that happen? This happens when there's tension in the glass. Why can that be? we are having a high viscosity, and then the homogenization will not be sufficient. This builds tension in the glass, and the glass breaks. So how can we tackle this problem? Once again, based on the recipe, we can change the flux, or we can add an additive. I will talk about the additives later. And based on the fusion technique, we can higher the temperature, because the higher the temperature is, the more fluid it will get, the more fluid the melt will get. And this is another way to tackle a problem like this. The second thing how this can happen is a non-dissolved particle. There's a particle somewhere in your glass, and along that particle, the glass will just break. This is the same effect here. You have the tension in the glass and it breaks. And based on the recipe, you will have to have a look on the fusion flux that is used. And based on the fusion technique, you can as well have a look at the temperature, but also on the fusion time. What happens when there's non-sufficient homogenization, but the glass doesn't break? Then you will get something like this here. You have a graph that is showing concentration and the date and time of measurement of different samples that were done. And you can see that I'm having a sky full of stars there, and I actually want the measurements to be somewhere between these red bars. So it will just have very poor precision there. So how can I tackle this problem with my flux? We already saw that the viscosity in melt decreases with increasing metaborate part. So the more metaborate is in my flux, the less viscous it will be in the melt. So the homogenization will be easier for a machine or a human to do. And it will also be easier to dissolve the sample in the melt. What does that mean? The fluxes that contain a higher tetraborate part, they are rather suitable for easily dissolvable samples, like samples that do not increase the melt's viscosity. But as well, we can have a look at the fusion technique there. When we are able to fuse these kinds of samples with higher temperatures, we might as well use fluxes containing a higher part of lithium tetraborate, even though the sample might not be easily dissolvable. So I have a small example here for you. We are having a look at a feldspar sample containing a lot of silicon dioxide, and we are having two preparations that only differ in the flux that was used. We are having one time a preparation 8 grams of our FXX65, which is a flux that contains 66% of lithium tetraborate and 34% of lithium metaborate, so more tetraborate than metaborate. And it was fused with our FLUXANA Vitriox electric using the A0 program, which equals 1200 degrees Celsius. And then we did the same sample, the same dilution, same machine, same program, but with another flux where we are having a higher part of lithium metaborate and a lower part of lithium tetraborate. And what we can see in the results is that the result for silicon dioxide and also the other components that we looked at with the FXX65, so more tetraborate, this is very poor. The standard deviation is very poor, and we can see we have results from 62% to like 84%. And this is just, not usable. This analysis is just not usable. So then we exchanged the flux, and what we see here is the influence the viscosity has on the fusion. We have a lower viscosity, now we can agitate properly, everything is dissolved, and we get a very nice standard deviation here, very nice precision in the same sample, using the same machine, at the same temperature, like all parameters the same, but a way better outcome here. So let's move on to additives. Additives are like non-wetting agents are used when you are having a low surface tension in the poured melt. So this can be due to the flux. What will this result in? It is sticking and breaking. Like the bead is very flat inside the mold, and at some point it will just break. And here we can see this is the first time we cannot do anything about it with the fusion technique. We can only tackle this problem with the recipe we are using, and we can either change the flux or we can add an additive. And what we see here is that the more metaborate part will be in your flux, the more it will become necessary to use additives in your preparation. So for high lithium tetraborate parts, it will not be necessary to use additives, but as soon as you are having the same or a higher lithium metaborate part than lithium tetraborate part in your flux, it is very likely that you will need additives to just get a stable, non-sticking and breaking bead there. The problem with the surface tension can also come up due to the sample composition. There we have the same effect. The bead is sticking, the bead is breaking, the bead is very flat. And here we can only handle the problem by using an additive like a non-wetting agent. So these elements, chromium, manganese, iron, cobalt, nickel, copper, those are the elements and components of samples that do these nice colors, but also cause low surface tension and then sticking and breaking. So if you're dealing with these kinds of elements in your fusion, you for sure from a certain concentration will need some additive there. What are non-wetting agents? Non-wetting agents are halogens. For example, bromine and iodine are used very frequently, and these increase the surface tension, so they will compensate the problem we just saw with the sticking and the breaking. What does that look like? We are having an example here of a melt that contains copper. That's why it's so nicely blue. And I first did a fusion without a non-wetting agent. And we can see that the bead is very flat and that it broke in a way that it cannot be used at all. Then I did the same sample, same fusion with 10 drops of lithium bromide solutions. And we can see here that the bead has a very nice shape. The bead didn't break. And as with everything, there's also a too much. So if we add some more drops of the halogen solution here, we get something that we would call a half moon. So this is too much. And the, and the bead will shrink in the mold that much that it cannot fill the mold anymore. Now there are some samples where you're having the problem that you have either this or that. So either you will have a break or you will have a half moon, and you will never get the exact amount of halogen you will need to get this kind of nicely bead. Then keep in mind that in XRF it's only important to have the correct ratio, and that means that if you just hire the amount of sample and your flux, you will be able to fill the mold again here. How are we adding additives? Additives can be already present in the flux, and they can be added as a powder or as a solution just by adding small drops. So this all sounds like very nice. Our beads are not sticking and breaking, but still we can have some trouble later there. So be careful, because these halogens we are using, they generate line overlaps in your measurement later. So be careful of that. I'm having two examples here. One time we are having the bromium alpha line that overlaps with aluminium K alpha and magnesium K alpha. We can see it in the graphics down here. The black one here is a limestone sample that was fused without bromide, and the red curve displays a sample that was fused using bromide, and we can see that the aluminium K alpha peak is significantly higher here. The same goes for the magnesium K alpha peak here. Again, same sample, one time in blue without bromide and one time in red with bromide. And also here, we can see an increase in intensity here in this peak due to the bromide concentration that is there. Now we could say, okay, then let's just use some other halogen, for example, iodine. But the iodine L-beta 2 line overlaps with the titanium K alpha line. We can see it down here in this graphic. The red line displays a sample without any titanium and any iodine, and the blue line here shows the same sample not containing any titanium, but some iodine was added. And we can see here that it actually looks as if there is titanium, because the iodine L-beta 2 line is directly under the titanium K alpha line there. So be careful about that. Also, there are some absorption effects possible due to the add of these halogens. Here we are having a limestone sample again, and lithium bromide solution was first not added, and we will get a concentration of roughly 52.5. And the more bromide was added to the sample in more preparations, we can see that the concentration of the main component decreases significantly. And this is an absorption effect that is caused then by the additional bromide we added into our prepared sample here. So now we talked a lot about problems, but that wasn't like our aim, right? We wanted to know, like, how do we get this? How do we get a very nice fused bead? So first of all, we are dependent on our sample. There are samples that are not critical at all. There are samples where you don't need to think about additives or using some special flux. Then you will be totally fine and you are very lucky. But if your sample is somehow critical, there are two things you have to think about. And one crucial thing is your fusion technique. And the other crucial thing is the preparation side. So let's first have a look off topic on what we already said about the fusion technique. We already talked about temperature. This to adjust the temperature can be necessary. To adjust the fusion time can be necessary. Cooling conditions, very, very crucial. Have a look on your cooling conditions when you're having problems with crystallization. And platinum wear. When your platinum wear is not in a good shape, maybe just exchange it for platinum wear that is in a good shape. When you're having scratches, it will cause crystallization. It can cause breaks as well. So this all has to be somehow optimized there. And then on the preparational part, We are obviously, what we didn't talk about is we also have the dilution. So the dilution also plays a big role in the preparation. And then we are having, of course, what we talked about today is flux and additives, also two main parts of that are important to get a nice fused bead. And we see this huge process here, and it doesn't even have all the different parameters that are influencing your fusion. And we only talked about those two today. So be careful and keep in mind that there's way more to the process than we just talked about. So we almost reached the end. So let's have a look on what we just talked about. So fusion is a complicated process. And we saw that a lot of different parameters are affecting each other, and you always have to have a look at the recipe and the fusion process. And then this leads to the next point, which is which flux is suitable is dependent on both your sample and the process. So you always have to have a look on both. There are some laboratories that always use the same flux for each and every application. And that's fine as long as it works, because there's a lower risk of confusion. If you are using another flux for each application that you're doing in your lab, the risk of confusion is way higher. But that also means that your fusion machine or your muffle furnace or whatever you're using to do the fusion has to be optimized, and there has to be the possibility to even optimize it, to go higher with the temperature, to get a better agitation there, and all the things, the cooling, the timing, everything we talked about in the last few slides. And then last but not least, it's the non-wetting agents, and they can prevent the sticking and breaking, but please be careful. The line overlaps and the absorption effects, they are real, and you have to consider them in your calibration. So all in all, you have these three things that you have to take care of. You have the flux, you need the suitable flux, you use additives whenever necessary and not when they are not necessary. And then you need a good fusion technique, and then you will be fine. Then the beads will come out just as you expect them. So first of all, thank you for your attention. That was quite a big topic for today. Don't miss our new webinar in January, so already next year. You can have a look at the topic now while I'm having a look on your questions. All the questions that I cannot answer now due to timing, I will answer per mail later. So here's a nice question. Which will be the better flux for XRF preparation? How can we find an equilibrium between glass forming and with melting and viscosity? So that's basically the whole problem we are facing here. The flux that have a better glass forming ability are also the ones that have a higher viscosity. So in the end, this is very dependent on your sample, and when the sample has glass forming ability itself, then you can also go for a flux with less glass forming ability and maybe lower viscosity. But if you are still having some problem there, maybe you can have a look at the fusion process itself, because then you can also lower the viscosity in the melt by having a higher temperature, for example. Or you can mix better by just hiring the agitation speed. So this will be then the part where you can actually never find an equilibrium between the glass forming and melting and viscosity there. You will then have to adjust the fusion process if you are having problems with all of these different things. So another question is if salmon samples have glass forming components. Yes, salmon samples contain roughly 20% of silicon dioxide, but the main component is calcium oxide, which will not be glass forming. So a cement will not be enough to go with fluxes that contain very, very little lithium tetraborate. So there you will have to be careful, but it will not be a problem probably to use something like our FXX65, which has 66% lithium tetraborate and 34% lithium metaborate. Something like this works perfectly with salmon samples. Maybe another word to exchanging flux. Please keep in mind when you're already using one flux and you are having a calibration with it, it is very hard to exchange the flux in between a process. So this is always something you have to think about before doing a method like this. All right, I have a look at the clock and I see that we already overdid it a bit. All the questions that were not answered until now, I will answer in mail. So you don't have to send me a mail. I have all your email addresses with me and I can then answer all of your questions per mail. Thanks again for your attention. Since this is the last webinar in this year, I can wish you already a nice holiday season and a very nice and happy new year. And please stay healthy and see you next year, hopefully.